Hello, everyone. Welcome to this session of ICM, where we're going to hear about a fascinating line of work on algorithmic discrepancy. Our speaker is Nikhil Bansal, who is the Patrick C. Fisher Professor of Computer Science at the University of Michigan. Nikhil works in the design and analysis of algorithms, as well as related areas in discrete math, machine learning, combinatorial optimization, and complexity. He's won numerous Best Paper Awards for his work, as well as a number of grants, and serves on the editorial boards of the Journal of the ACM and Theory of Computing. Nikhil will be giving the talk live. If there's time at the end for Q&A, you can type your questions into Discord, and I will read them out to Nikhil, or he can possibly answer them afterwards. Use channel 6 for section 16, Control Theory and Optimization, for your questions. Nikhil, take it away.
Okay, thank you, Salil, for the introduction, and thanks also to IMU for inviting me. It's a great honor. So I'll be talking about discrepancy theory and some recent algorithmic progress on this topic. Good. So a traditional way to define discrepancy is the following. There is a universe of elements 1 through n, and we are given some subsets S1 through Sm on this universe. And our goal is to color these elements red and blue, so that each set is colored as evenly as possible. Ideally, you want to balance these sets perfectly in terms of red and blue elements. So to be a bit more formal, we can think of a coloring chi, which colors the elements -1 and 1. And then if you look at a set and sum up all the colors of elements in that set and look at the absolute value, it measures the imbalance. And we call the discrepancy of a coloring X as maximum overall sets of what this imbalance is. And we are interested in sort of the best possible coloring, right? So there are 2 to the n possible colorings, and we want to understand what's the best possible coloring of this set system. And that's called the discrepancy. Another sort of way to think about it a bit more generally is that you're given some matrix A. So if you think of this previous set system setting, you can think of the incidence matrix where the rows correspond to sets and the elements to columns. And basically, you're multiplying this matrix by a +1, interested in the infinity norm, the smallest infinity norm over all such vectors. Right? So you can quickly see that this is exactly the same definition as we saw before, and this is a bit more general because you can have arbitrary matrices. Another sort of way to view discrepancy is like a vector balancing view. So you are given vectors. Again, these are columns of your matrix A. And you want to color these vectors or multiply these vectors by -1, 1. And so that when you look at the sign sum of these vectors, no entry of this sign sum is too large. So again, it's an equivalent view. So when you first see this definition of discrepancy, it might seem a bit artificial and sort of made up. But this sort of comes up in many, many areas in several disguises. And roughly the reason is, so the thing that discrepancy is essentially trying to capture is how well we can partition 2 sort of set of objects or points into 2 similar parts. Right? So like one way you can use discrepancy is, if you can break an collection of objects into 2 parts which are very similar, you can do this recursively and kind of sparsify your system to get something that's equivalent but much smaller. So this kind of theme arises in various different areas. And again, I won't talk much about these applications. There are like even lots of books written on this topic. But discrepancy also arises in many different unexpected ways. So one application which I particularly like is to sort of the rounding problem in approximation algorithms. So here, again, you're given some matrix A, and let's say some fractional solution X to some system AX equal to B. And often in algorithms, we are interested in rounding this fractional solution, maybe which lies between 0 and 1, to sort of a 0-1 solution, where the entries are 0, 1. So let's call this X tilde, this rounded vector. And you want to do it in such a way so that the error you introduce when you round X to X tilde is not too large. Right? So maybe you are interested in minimizing this L infinity error. And a very beautiful theorem of Lovett, Spencer, and Westergombe is that there always exists a way to round X to some X tilde, which is integral, so that your error is at most what's called the hereditary discrepancy of A. So again, I won't define what hereditary discrepancy is. It's a slight variation of discrepancy. And again, roughly the idea is, so here is an intuition why this might make sense. So suppose you had a fractional solution to ax equal to b, and suppose for a moment x was just all half vectors, right? And you want to make it either 0 or 1. Then if you had a low discrepancy solution y, so ay was almost 0 for some plus minus 1 vector y, you can use sort of this y vector to guide you whether to round entries up or down, right? So in particular, if I define my x tilde as x plus y over 2, so this will be a 0, 1 vector now because y over 2 has entries plus half or minus half. And if ay was 0, then you can easily check that ax tilde is also close to ax. Right? And this was for half integral things. And if you do sort of bit by bit around them. Another sort of surprising thing is like many classical problems in mathematics can be cast so often in a surprising way using a discrepancy theoretic language. So a famous example is this Cadison-Singer problem, which is related to a lot of areas and received a lot of attention recently. So here the problem is the following. You are given rank 1 PSD matrices A1 through AN with sum up to identity. And let's say each of them has a small operator norm. And that's the Cadison-Singer question as whether there are signs, plus minus 1 signs xi, so that if you look at the signed sum of these matrices, the operator norm is like strictly less than 1. So if you picked all xi's to be 1, since these ai's sum up to identity, clearly this is 1. So the question is really, can you pick different signs to even get a small improvement like 0.99? And this was open like for almost 50 years. And in a major breakthrough, Marcus Spielmann and Srivastava actually showed you can do much better and in fact get a bound of square root epsilon, which is also tight. Right? So yeah, so often discrepancy arises in all kinds of things. And I won't have much time to talk about applications, so I'll sort of focus on the basic techniques. And I'll also just focus want to look at the sign sum of vectors instead of more general objects like matrices. So sort of the theory is most well developed vector setting, and this is what we'll focus on. Okay. So this was the definition. So let's look at what we can do. So whenever you're given a discrepancy problem, one thing that one can always do is do a random coloring, right? Just take your elements and color each element independently, plus 1 or minus 1 randomly. So let's see what this gives us. So then if you had some any set system with m sets, it's easy to see that a random coloring will have discrepancy about square root n times root log m. And this is because if you look at any particular set or a row, it could have up to n elements. So if you do a random coloring, its standard deviation will be about square root n. And we know by standard Chernoff bounds or Gaussian estimates that the probability it's about c times root n will be e to the minus c square. So I can set c to be root log m and then take a union bound over all these m different sets, right? So this is a trivial application of the basic probabilistic method and union bound. So yeah, so this bound always holds. So discrepancy sort of, so this is always a baseline solution, right? And what we are interested in discrepancy is whether can you beat this? This is only when, that's what makes it interesting. So notice a random coloring is like, I mean, it does reasonably well. It gets root n, but it's also not very satisfying because for one, it's ignoring, any possible structure that you might have in A, which you can maybe use to get better coloring. And perhaps what's more surprising that even if you don't have any structure in A, sometimes you can get better results. And so I'll explain what I mean by this. And so to do this, in this talk, I'll just focus on sort of two canonical problems in this area. So first problem is what's called the Spencer's problem. Here you are given n elements and let's say n sets just for simplicity. So m is equal to n. Now, if you did a random coloring, then by this previous argument, you will get root n root log n discrepancy. And it was a long-standing question of Erdős. So he conjectured that you should be able to do better and get like some order root n. And this is also the best possible. You can't hope to do better than root n. And this was proved then in a remarkable result by Spencer in 1985, which is a sort of a celebrated result in this area. And it's interesting for several reasons. So first, notice that this root n avoids this root log n loss due to union bound, right? So it's kind of beating this union bound, which is always interesting, whenever you can do this. And again, a priori, there is no reason why such a result should exist, because often probabilistic method, actually gives you the right answer. And in fact, in this setting, if you do a random coloring, you will actually incur this root log n thing. So these root n colorings are very special, and actually they form only an exponentially small fraction of colorings. So you have to be sort of very careful in how to color these elements. So more importantly, Spencer developed what's called a partial coloring method, building on some work of Beck from the 80s, which was based on probability and pigeonhole arguments. And this method is very general, and I'll describe it in the next few slides. And you can apply it to a lot of problems, and sort of one of the major techniques in the area. So Spencer proved his result using probability and pigeonhole arguments. There was a different proof by Gluskin, other side of the Iron Curtain, which was not so well known in the West for a long time, based on a convex geometric approach. And actually, I'll use the opportunity here to talk a bit about this elegant, nice proof. So that was the first problem. The second problem we'll consider is what's called the Beck-Fiala setting. So again, here, let's say there are n elements and n sets. But now we have a restriction that each element lies in at most t sets. So if we go back to our matrix, it's saying that your matrix is t column sparse. It's a 0, 1 matrix with at most t ones in any column. So let's see what happens here. So again, if you do a random coloring, you can still get a root n discrepancy, because we don't have any control on what's the size of a set, right? A set could still have order n in root n discrepancy. But notice that in this case, a typical set will have size about t, because it's an n by n matrix, and there are each column has at most t ones. So there are n times t ones in this whole matrix. So by averaging, a typical row will have size t, even though some rows can be very large. So a famous conjecture, which is still open due to Beck-Fiala, is that the discrepancy should really be the square root of a typical row size, which is square root t. And what one can show, so using the partial coloring method that Spencer invented, you can get actually quite close to root t. So you can get a root t log n, and we'll see this later. And this was by Banaszczyk in 97 to improve this log n factor to a root log n factor. And so these two techniques, partial coloring method and Banaszczyk's method, are sort of the two major techniques in this area for a long time. And we'll see later how they have evolved. Okay. And I just want to mention one more problem, which is one of discrepancy, which is a generalization of this Beck-Fiala setting. So this is called the Comlosh problem or the conjecture. So the problem is the following. You are given n vectors, let's say in Rm. We should think of m as n just for simplicity if you want. And each of them has a unit length. And the Comlosh conjecture says that given any such vectors, you have discrepancy at most order 1. And what Banaszczyk really showed was a square root log bound here. So notice this Comlosh conjecture generalizes the Beck-Fiala setting, because if I multiply this matrix by 1 over square root t, each column will have Euclidean length at most 1, right? So it's up to root t scaling, sort of a special case of Comlosh conjecture, right? So the state of art is root log m, and conjecture is order 1. Good. So here's the plan for the rest of the talk. So I'll begin sort of with a geometric view of discrepancy, which will see why convex geometry ties in. And then I'll talk a bit about these two techniques, which were classical in this area of partial coloring and Banaszczyk's method. And as we'll see, these two techniques were sort of existential, like they showed the existence of a coloring, but they didn't give you any clue on how to actually find one algorithmically, like efficiently in polynomial time. And for reasons that we'll see, they were also believed to be inherently non-algorithmic for a long time. But recently, there has been a major progress on both these methods. So in fact, we now know how to make both these methods completely algorithmic. And in fact, many more results and ideas have come out from these algorithmic approaches. So I'll describe these algorithmic approaches, giving sort of a high-level idea. So I won't say much about the proofs. So the proofs can actually be found in the accompanying survey article. So I'll just focus on the high-level ideas. And then I'll talk about some open questions and recent directions. So good. So let's look at how geometry naturally enters the picture in discrepancy. So again, given a matrix A, where variables are these x1 through xn, the following. So it says that for each row, right? I'm looking at the set of all x, so that ax is less than t and at least minus t. So it's between minus t and t. Right. So you should think of some polytope like this. And notice as I scale this t, right, this polytope gets bigger and bigger. And if you think for a moment, you'll see that a discrepancy of a matrix A is exactly the amount by which I have to scale this polytope until it contains some point which has all +1 -1 coordinates. Right? This is really a tautology, it just follows from definition, but it's a useful geometric view. And once we phrase in this geometric way, we can try to invoke all kinds of results from geometry. So what Gluskin actually showed is the following result, which is sort of very nice on its own. It says the following. So if you have any convex body P in Rn, which is symmetric with respect to origin. So if x lies, then minus x also lies in P. And if it has and suppose P has a large Gaussian measure. So by large, I'll mean the Gaussian measure at least, let's say 2 to the minus n over 100. It's large in the sense, if you compare to the -1 cube, so the Gaussian measure of this cube will be about the measure of the unit interval raised to the n. So think of this as roughly 2 to the minus n. So it's much larger than the volume of the cube, even though it's exponentially still very small, right? So if you picked a random Gaussian, you're very, very unlikely to fall in this P. So what he showed is that if you take it contains a point which has -1, 0, 1 coordinates, and at least n over 2 of them are +-1. So it's a nice geometric fact. And actually the proof is quite easy. And in fact, the proof goes, for those of you might have seen, it's similar to this Minkowski's theorem's proof, which is again based on the pigeonhole principle and says, if you have any symmetric body with volume Lebesgue measured 2 to the n, it has some non-zero sort of lattice point in the standard lattice, right? And again, if you have seen this proof, you'll see that, it just shows you the existence of such a point. It's a very beautiful pigeonhole argument, but it gives you no clue how to actually find such a point. And in fact, Minkowski's theorem is very closely related to the problem of finding short vectors in lattices. And in fact, we don't know of any good algorithm which gets a reasonable approximation. And it's actually believed that it should not be possible. A lot of lattice-based cryptography, for example, is based on that. So yeah, so somehow these problems can be surprisingly hard to make algorithmic. So this is sort of one reason why, results like Gluskin's were also believed to be inherently non-algorithmic. And we'll see how Gluskin applies to discrepancy. So that's why discrepancy was also believed to be non-algorithmic. Good. So let's see how this gives the partial coloring lemma of Spencer. So here is what the partial coloring lemma says, that if you give me any matrix A, you can find a coloring X with the following properties. So AI is the ith row of matrix A. So the discrepancy of the ith row is at most lambda I times the L2 norm of the ith row. And you can pick any lambda i's. You can pick different lambda i's for each different row as you like, as long as they satisfy this following global condition. Right? So we'll parse in a minute what this means. Yeah, but it's just saying you can pick any lambda I and you can demand partial coloring, which has discrepancy at most this much. And again, by partial, I mean at least n over 2 coordinates are -1, 1. The others are, let's say, between -1, 1 or 0. Okay, and again, the proof of this, once you have Gluskin's theorem, is just immediate. You just look at the appropriate convex body, which in our case would just be this, right? Like you just want X so that it satisfies your discrepancy constraints. And really, this condition here is basically ensuring that the Gaussian volume of this body is large. Right? So this will just follow from Gluskin using a standard computation. And the amazing thing about this condition is that, notice it's very powerful. So for instance, I can set omega n of my rows to have discrepancy very close to 0. Right? Because even if lambda I was like close to 0 or 0, this left-hand side is only 1. So I could set like n over 20, let's say, lambda is to be 0, which is really amazing because, for example, if you go back and think of a random coloring, there is no way a random coloring can get you even for more than 1 or 2 rows, like discrepancy 0. Yeah, so this is a very, very powerful result. Good. Yeah. So one drawback with this partial coloring is it's it only gives you a partial coloring, not the full coloring. But in many cases, this is okay because, like, if you go back to Spencer's problem, discrepancy. And then once you have a partial coloring, you can apply this recursively, color half the elements and so on. And this works for Spencer's problem because n is roughly decreasing geometrically as you go along. So the overall discrepancy when you get the full coloring is also root n. However, for some problems like the Beck-Fiala setting, this partial coloring to full coloring, you can lose a log n factor. Because again, let's see how this is applied to the Beck-Fiala problem, this partial coloring lemma. So again, you can that whenever you have a large set, so remember a set had typical size order t. So if a set was much bigger than t, you can just set its lambda to be 0. And you can show that this condition is satisfied. So basically what partial coloring lemma says is that you can find discrepancy root t per phase of partial coloring. Because large sets have 0 discrepancy and small sets have root t, order root t. Okay, but yeah, so you get a partial coloring with root t discrepancy, but when you iterate this over the log n iterations, you will incur this extra log n factor. And this wasn't known how to improve for a long time. Okay, so yeah, so partial coloring is very powerful and works very generally. So, right, so as I said, these results were sort of believed to be non-algorithmic because all the proofs went via pigeonhole arguments. So the first algorithms appeared in about 12 years ago. And they work for sort of special problems like Spencer, Beck-Fiala, and some other problems. And the main idea here was the following. So before we give the main idea, let's actually go back and look at random coloring, which we know is. But one way to view random coloring is the following. So let's say we consider the +1 - 1 cube, where each vertex corresponds to like a coloring. Right? So imagine we start where all the colors are 0. So each vertex is uncolored, and start doing a random walk. So maybe a discrete Brownian motion, and so on. So we continue, and whenever we hit a face of this cube, so if some variable reaches +1 - 1, we continue to walk in that phase. Right? So we fix that color and continue, and maybe more colors reach +1 - 1, we continue, and so on until we reach a vertex. Right? So if you think about it, this is nothing, right? So it's eventually ending up at a vertex, and you'll generate a completely random vertex because this is a fully random walk. Very complicated and painful way to view a standard random coloring. But the advantage is, if you think of it in this dynamic way, that you can apply you can control your random walk as you go along. So for example, if there was these discrepancy constraints that you don't want to violate for certain rows, then maybe as your walk gets closer to these constraints, you can maybe change the covariance matrix or modify it in some other way. So this gives a lot of flexibility. And this is what the first algorithms for these partial coloring did. They sort of slowed down the walk as it approached these, and using a certain semi-definite program and so on. So yeah, so this approach was a bit ad hoc and problem specific, but then later much simpler and more general algorithms were developed, which I'll quickly describe due to Lovett, Meka, and Rothfuss. Yeah, so let me describe this one algorithm, which is particularly elegant, called Lovett-Meka algorithm. So again, this is just the statement of the partial coloring theorem. So the algorithm of Lovett and Meka is the following. So again, you start from the, let's say, all zero coloring or some initial coloring. And again, you just start doing a Brownian motion and some small discrete steps to make it polynomial time. But now you do the following. So if your walk reaches a phase, so if some variable reaches -1, 1, sorry. So if some variable reaches -1, 1, you fix that. And okay, and the second step is if some row AI gets tight, so the discrepancy constraint becomes tight for that row, you kind of stick to this phase and or this constraint and keep walking in that subspace, right? So, right. So as your walk goes along, either you hit a phase or you hit one of these discrepancy constraints and you keep continuing. And what they can show is that, you know, this condition basically guarantees that these discrepancy phases are typically much further away than these cube phases. So what this essentially shows is that, you know, your walk will still continue once, okay. So as your walk goes along, every time it hits a phase, it kind of slows down because you're moving in one dimension less, and eventually it will like totally get stuck. And the point of the analysis is that, right, once your walk is like completely slowed down or stuck, it will reach enough +1, -1 phases. So it's a very beautiful idea. A second idea was by Rothfuss, who extended this result of Lovett-Meka sort of beyond polytopes or, you know, this discrepancy setting to the full Gluskin setting of arbitrary convex bodies. So again, just to remind you, this was the result of Gluskin. And the idea of Rothfuss is even simpler. So his algorithm is the following. And actually, this is the whole algorithm here. So you just pick a random point in the Gaussian space. So each coordinate is normal 0, 1. And now you just solve the following optimization problem. So yeah, so I sample this point Y. And then I try to find a point X star, which lies in the intersection of your convex body P with this +1, -1 cube. Right? And you can write this as a convex optimization problem, right? Because you're trying to minimize the Euclidean distance, and this is some convex set, which is the intersection of the cube and the body. And so that's it. So that's the whole algorithm. And what he shows is that this point X star, so by definition, right, it lies in the cube and it lies in your convex body P. So the only thing to show is that it will have a lot of +1, -1 coordinates, which is sort of what we want. And again, the idea is very beautiful. So it sort of follows from measure concentration quite directly. Yeah, so maybe I'll just give the high level idea. The point is that, you know, your Gaussian measure of this body P was much larger than the Gaussian measure of this cube. So by standard measure concentration, this point Y will be much closer to the body P than to the cube. So when you solve this optimization problem, most of the constraints that come will sort of be coming from this cube, right? And every time you get like a tight constraint from the cube, this means, you know, there is some +1, -1 coordinate that's sort of constraining it. And again, sort of, you can make this precise in a very clean way, and you can show that, yeah, most of the coordinates are +1, -1. Okay, so this was sort of some progress on partial coloring, and actually there have been lots of other results in this direction. So let me say a few things about, you know, how to go beyond this partial coloring or the Banaszczyk's method. So Banaszczyk had this very general result, which says the following. So again, you are given vectors v1 through vn of length at most 1. And suppose you are given any convex body K, which has Gaussian measure at least a half. Then Banaszczyk shows that there is always some +1, -1 vector X, so that the signed sum lies in, let's say, some constant scaling of your body. right? So it lies in K, let's say. And again, this was a very, very nice existential argument. In fact, sort of it's much more delicate and subtle than sort of Gluskin's argument. So I would highly recommend it. It's a very beautiful argument. And again, this is very general because let's see how this directly gives Komlosh or Beck-Fiala problem. So actually, let's look at Komlosh setting, which is more general. So there, we had unit vectors v1 through vn, and we wanted them to have small L infinity norm. Right? So you can just, so infinity norm corresponds to the cube, standard cube. And you just have to figure out how much to scale the cube so that its Gaussian measure becomes half, right? So you can see, because you have m dimensions, so root log m scaling will be enough. And that's it. So that gives the root log m bound, which is the best bound we know for Komlosh. Right? And again, as you can see, this result is very general, and by picking various different convex bodies, and you can get all kinds of results. Good. So the algorithms for Banaszczyk came out relatively recently. So for a long time after these partial coloring algorithms, we didn't know how to make Banaszczyk's idea algorithmic. But there are two results. So first, there was a result by myself, Dadush, and Garg, where we gave for the specific Komlosh setting and got a root d root log n bound. And then in a couple of years later, we could extend this to the more general Banaszczyk setting of arbitrary convex bodies. So let me give a few ideas about these things. And before we do that, let's go back to the partial coloring setting and see why we get the log n loss, right? Like we want to make this log n to root log n. So what can we do? So let's look at the Beck-Fiala setting. And recall there, the way we applied partial coloring was for large sets, which are bigger than typical, we set lambda to 0. So we wanted 0 discrepancy for them and root t discrepancy for the typical sets, right? And we applied log n phases of such things. So if you see what's happening over time in this algorithm, as long as a set is large, has size bigger than 10t, it incurs 0 discrepancy, right? And it only starts incurring discrepancy when its size falls below 10t. So one should think intuitively that, of size order t, right? Until then it has 0 discrepancy. So we should expect root t root log n, right? Because if you are actually doing a random coloring, this set would get a root t root log n discrepancy. Now, the reason why partial coloring loses is that, so this intuition is correct, but in partial coloring, the walk can be far from random. And the trouble is that once you walk in these subspaces, like in the Lovett Meka walk, you can introduce all kinds of dependencies. So for example, maybe once you're walking and you hit certain faces, maybe you're constrained to walk in this subspace where the x1 equal to x2 equal to xt. So what this means is that now if all these xt's, because they have to lie in the subspace, either all change by plus epsilon or by minus epsilon. Right? So, and this is bad because if maybe we had consisting of the first t elements, or if you look in this direction, e1 plus e2 till et, then for that, your walk is not looking random at all, right? Because all coordinates go by plus epsilon or minus epsilon. And these kinds of dependencies can really hurt you. So the key idea in this work of myself, Dadush, and Garg was a following sort of a smarter random walk, which says that you can design a random walk that looks random. And I'll make this precise what I mean, even if you're constrained to walk in any subspace. Maybe here is a picture. So suppose I'm constrained to walk in this subspace W perp, then I can do a random walk in such a way that, right. So so actually let's just look at these two properties. So suppose you're given some subspace W, which has some decent codimension, at least delta n. Then I want my walk to satisfy two properties. It should be in W perp, so this condition. And the second property that no matter which test direction I look in, this walk x, so that's my update step, right? The squared increment sort of looks like as if these delta xi's were independent. And this should happen for every direction. Right? So this is what we mean by sort of a smart random walk. Even if you have to lie in a subspace, you look random. And turns out one can actually do this by writing and solving a certain semi-definite program. So the root T root log and algorithm for Beck-Fiala is basically, you just do the sort of Lovett Meka type of walk. But once you hit a discrepancy constraints, instead of doing sort of the standard random walk in that subspace, you do this sort of smart random walk. Right? So you still need to solve a semi-definite programming at each step to generate these next steps. So it turns out, yeah, so you can get root T root log n. Okay, so let me in the next couple of minutes say a few things about the general Banaszczyk's theorem. And again, this is the statement of Banaszczyk's in its full generality. So again, just to remind you, we are given vectors v1 through vn of length at most 1, and some convex body of Gaussian measure at least a half. And Banaszczyk says that there is a +1 -1 coloring, so that the sign vector lies in some 5 times k. Okay, so when you try to make this algorithmic, the first sort of trouble you get into is so this coloring that we are constructing clearly depends on the convex body. If I change my convex body, the coloring in general will change. So when you try to look at it algorithmically, the first question is, how is this convex body even specified to me? Right? Because just specifying a general body to any sort of reasonable accuracy would already take exponential size. So sort of doesn't make much sense for polynomial time algorithms. So a key insight was in an initial paper of Dadush, Garg, Lovett, and Nikolov. So what do I mean by this? So let's look at the quantifiers here. So the theorem is saying, so if imagine there are 2 players, one of them picks like a bad convex body to hurt me, and the other player is trying to find a good coloring. Right? Right. So Banaszczyk's theorem is saying no matter what the first player chooses, which body, the second player can always find a good coloring. So this suggests that if you view this as a game, you should be able to like flip the quantifiers if you allow a distribution on colorings, right, by the min-max theorem. And indeed, this turns out. So yeah, so one can show that there exists a universal distribution D on colorings X. I'm allowing mixed strategies for colorings, which will simultaneously work for every convex body with measure half. Max. And if you play with this, what this turns out, since you need a distribution of coloring that works for every body with half, essentially it turns out that there is some distribution in coloring X, so that this signed sum, this random vector, is order 1 sub-Gaussian. And recall this. The definition of sub-Gaussian is the standard one. So it just means if I have a random vector, then in each direction, it looks like a Gaussian when I project it in any direction. Right. So the nice thing about this formulation is that there is no convex body K anymore. Right? It's purely a question about constructing a distribution on colorings, which gets you these signed sum vectors, which are sub-Gaussian. Good. So, right. So this is just restating what our goal is now. And let's just look at 2 special cases. Suppose your VIs were orthogonal, right? So the inputs to the Banaszczyk's theorem were orthogonal vectors. Then actually a random +1 -1 coloring will work. And why is that? It's very easy to see. Because coloring Xi. Then this sign, so y is my signed sum vector, which I denote. And if I look at it in direction theta, right, you can write it like this, right? And since these xi's are random, this will look like a Gaussian with variance sum of squares of vi theta whole square, right? But since these vi's are orthogonal and this theta is a unit test direction, this is at most the length of theta, which is at most 1. So yeah, so the point is, if my vectors were orthogonal, this trivially works. On the other extreme, suppose my vectors were sort of all identical or pointing in a similar direction, then random coloring will be very bad, right? So for example, if they were identical vectors, if you just did a random coloring, you would have omega root n sort of variance in direction or standard deviation in direction of V. And in this case, you actually need to do something careful and a dependent coloring, carefully balancing plus ones, minus ones. What's called the Gram-Schmidt walk, inspired by the Gram-Schmidt orthogonalization process, because you somehow want to capture both these cases, right? So you want to handle dependencies, like if your vectors were sort of had dependencies among them, but you also want to be random in case sort of if they were close to orthogonal. So one can actually design a random walk process, which actually nicely interpolates between these two extremes. So in our original paper, we showed that this process was order 1 sub-Gaussian. And subsequently, there was a tight analysis given by Harshaw, Peng, Xavier, and Spielman, which actually showed it's 1 sub-Gaussian, which is the best one can hope for. Okay, so let me conclude with some open questions in this area. So first, there are sort of many problems where we still have gaps. So again, I didn't talk about too many problems, but for this sort of famous Komlosh problem, for example, we have this 1 versus root log n gap. Right, and there are many more which I discussed in the survey. Another setting where we don't know much algorithmically is for prefix discrepancy. So here, actually, Banaszczyk in a recent result extending on his previous work showed you can look at a prefix version of the Komlosh problem where given vectors with length at most 1, there is a coloring so that every prefix of the signed sum has low discrepancy of root log n. So again, Banaszczyk's technique is completely sort of existential. But for this problem, the best algorithmic bound we know is only log n. And in fact, as far as we know, even existentially, one could get to order 1. So the previous sort of algorithmic techniques, we don't know how to make them work. And this is a very nice question because it would have to all kinds of other related problems in discrepancy. Another setting that was recently considered was the online setting where vectors arrive 1 by 1. And again, the best bound here is order log n by a beautiful algorithm due to Alweiss, Liu, and Sony, based on what they call a self-balancing walk. Right? So in the online setting, when a vector arrives, you have to color it right then without knowing what happens in the future. And yeah, so they could get a log n. And a big question is whether you can improve this to root log n. And if you could do this, this would also solve the prefix Komlosh problem, because inherently the online problem is automatically ensuring that every prefix is also having a low discrepancy. Right? So this may be one way to attack this prefix discrepancy. Another setting that has received a lot of attention is the random case. And here, so one kind of canonical result in this area is, let's say if we go back to the Spencer setting, and if you are in the case when the number of elements n is sort of bigger than m log m, where m is the number of sets, then actually you can get discrepancy, which is just 1, right? Which is quite remarkable. And yeah, so this is for the random setting, let's say where the sets are random. And these arguments are based on sort of statistical physics / careful second moment computations. And it would be very interesting if either one can make these algorithmic or maybe rule out that algorithms can exist, maybe even for certain classes of algorithms. And finally, another very nice question is sort of in matrix discrepancy. So there have been a lot of work on trying to extend these discrepancy settings to the matrix version. And one question that I really like is this algorithmic Cadison-Singer, which is completely open. So the result of Marcus, Spielman, Srivastava was based on sort of these interlacing polynomial techniques, which again are existential, and we have no clue how to make this algorithmic. So let me stop at this point. Thank you.
Thank you, Nikhil, for the wonderful talk. I'm afraid we don't have time for live questions, so just we'll direct people to the Discord channel 16 if they want to ask questions.
Great. Thank you.
Thank you.